All right, here we have lesson 7, more linear modeling. We are still doing the same thing we were doing the other day. Okay, we have to remember there's two most important parts of a linear function are the average rate of change, which is the slope. Okay, it is how the output is changing relative to the input. We also always want to know the initial starting value, or the y-intercept. These two things are going to be very important in terms of making equations and function rules that are going to be linear of sorts. So let's take a look at this one. The cost, C, in dollars of running a company that produces textbooks, T, can be modeled using the linear function C of T. Again, that notation here is C of T. And that equals 17t plus 3,108. So C stands for the cost, and T stands for textbooks. Okay, and this equation is something that is making it, or it's telling us for every textbook that is going to be produced, how much money this company is going to make. All right, so how do you interpret the fact that C of 10 equals $3,278? Or actually, it's not how much the company's going to make, it's how much it costs to run this company. Okay? So how do we interpret this C of 10 equals 3,278? What does this mean? Okay, remember, whenever we have the number here, the C of something, that number is what we would have put into the equation where the variable was. So if we want to backtrack a little bit and we want to figure out what C of 10 is, it would have said C of 10 equals 17 times 10 plus 3,108. So C of 10 equals 170 plus 3,108. And so therefore C of 10 equals 3,278, which is no surprise because that's exactly what this question told us. So what does this mean? Well, it is, what was T again? T was textbooks. So this value here was T. So this means the cost of running a company, if we produced 10 textbooks, the cost of producing 10 textbooks is $3,278 to run that company. Awfully expensive to create 10 textbooks. All right, so let's look at this next part. Give a physical interpretation for the two parameters in this equation. The parameters, again, it tells you they are number 17 and 3,108. Okay, but more importantly, the parameters in general, if it didn't tell you what they were, the parameters, remember, are the slope and the y-intercept, the b value there. So the m and the b, as far as y equals mx plus b. Okay, we talked about parameters briefly last lesson. The m and the b are the parameters. They're the two things that are really going to make this linear equation what it is. Okay? So what is a physical description of this 17 and this 3,108? All right, let's start with the 3,108. That is the starting value for this function. In other words, it's going to cost my company that much whether or not I make a textbook or not. Think about it. If you put in 0 for T, in other words, I made 0 textbooks, then I have 17 times 0 plus 3,108. So the starting value when x is 0, what y is 3,108. This is the y-intercept. So it means just the daily cost of my company is going to be $3,108. I got to pay employees and rent and electricity and all that stuff, and it's going to cost me that much. Okay, so the 3,108 represents the cost of running the company before any textbooks are made. All right. So what does the 17, the other parameter here, what does the 17 mean? Remember, the 17 is the slope, right? And slope is also called the rate of change. Okay? So what is that 17? Usually we consider slope a fraction. So what if I put this as 17 over 1? What would that mean? How is that changing? That's the change in y's over the change in x, right? In other words, the change in output over the change in input, right? Or we could call it the change, in this case, of cost over the change in number of textbooks. So as the textbooks go up by 1, the cost goes up by $17. So this value here, the 17, represents the change in cost of the textbook, or change in cost as, let's say, as the number of textbooks change. Okay, it is the rate of change. All right, so these are our two parameters, the starting value and the slope or the rate of change. Okay, and that's what these things mean. Let's look at this. This is a pretty cool question. It says the population for Syracuse, New York is given for 3 years in this table below. So let's just kind of evaluate this table real quick. One of the first things we should always do whenever trying to tackle a question like this is take a look at the stuff that's in the table and try and make some sense of it. Okay? Over here we have years. Year 1910, the year 1920, and the year 1950. The first thing I kind of realize about that is that these years are not going up by 10 every time. Okay? There's not some sort of pattern happening in the table. In other words, there's a bunch of kind of missing data in there. So I can't make a linear necessarily guess as, well, maybe I could make a guess, but I don't know if this information is going to create a linear model or not. How about over here? Well, this looks like it's going from, let's see, this is almost 140, and that's almost 170. So this looks like it's going up by maybe 34,000 or so. And then going up again, this looks like it's going up almost 50,000 from here to here. So again, there's not a constant rate of change necessarily going on here from one thing to the next. So that's one of the things, there's kind of an idea that I'm noticing about this table before I really go anywhere else with this. All right. So now let's look over here at the first question part. Using 1910 as t equals 0, so t must be for time, we're going to create a linear model from the first 2 data points. So this data point and this data point. Okay? From the first 2 data points, to predict the population P, so this is going to end up being P, and this as a function of the number of years since 1910, and it already told me years was T for time. So we have data points, T comma P, okay? So 1910 comma the population over here, 137,249. But it's telling me instead of using 1910, we're going to call that 0. So let's look down here at this table. we're going to look at 0 as the year 1910. Okay? So let me write that underneath, just so we keep this straight. 1910 is going to be at 0 here. And at that point, the population is 137,000. So a little bit less than 150, a little bit less than halfway, so about right here. All right, so the next data point is at 1920. So let me look down here, 1920. So would I go to here? That would be my first thought, would be I go all the way over here to 20. But the reality is I'm going up by 10 years. So if this one was 1910, then plus 10 more years, right? I know I'm going up by years because there's my label down here, time in years. So 10 more years would bring me to 1920. So actually my point is here. Okay, so now let me go up from 1920 to the population is 171,000. So I'm closer to this 200,000 mark, about 3/4 of the way up, so maybe somewhere around here. It's a pretty good estimate. Okay, and it says in this question that to create a linear model from the first two data points. So now I have the first two data points, 1910 and 1920. Okay, and I look over, and this is about where they're at as far as population goes. And so now I can create a linear model. So let me get out my line making tool here and see what I can do for a line starting here and going through that point, and I'm going to continue it that way for a while, like that. Okay, and since it's a linear model, it would continue to go in that direction. I'm going to put an arrow on the end there. I wouldn't put an arrow on this side because we're not going backwards from 1910, hopefully. And so now what do I want to do? Let's see. So that's good. So that's a function, a linear function since 1910 for the population. Okay. So question down here says, if this model is used to predict the population of Syracuse in 1950, will the model overestimate or underestimate the actual population? Okay, so 1950. I'm looking for so on my table up here, I see 1950s right here. And the population should be in 1950, 220,583. So what I need to do is on my table down here, I need to find where 1950 is. Remember, we're going up by, this looks like it's increasing by 10 years each time. So let me count them out. So if this one was 1910 and 1920, then 1930s here, and 1940s here, and 1950 would be this one. So 40 years after 1910. Well, that makes sense. That's 1950. Okay? So I'm going to start here at 1950, and I'm going to go up all the way up until I hit my line. Okay? And now I'm going to go, here's a point right there. I'm going to come over. And it looks like if my lines were kind of straight, I'm somewhere around 300,000 people for population in the year 1950. But when I come back over to my table, it tells me I'm only supposed to be at 220,000, so somewhere like closer to here. Probably about here. Okay, so it looks like my population line, this model for the population, this linear model, is going to overestimate in the year 1950 what the population is for Syracuse, New York. So a linear model may not be the best model used to show the population for a city, and especially in this case for this city. Some things, some interesting facts about this. These were actual numbers from 1910 to 1950. The population did seem to rise from 1910 to 1950. And then after 1950, the population started to actually plummet way down. And up into the 2000s, the population did not start to level out until around 2007 or so, 2008, when it started to kind of just float around the 140,000, 135, 140,000 mark, around there. So we've actually lost close to 100,000 people since 1950. We've almost halved the size that we were in 1950, which is kind of interesting. So I'm sure some sort of economic events of some sort happened in the Syracuse area to boom the population back then, and I'm sure other economic disadvantages and things have happened since then to create the serious drop. So anyway, that's what I got. We're going to look at more linear modeling next class, and we're going to just continue to kind of push these ideas and see how these real-world events can be modeled in a linear way with functions. All right, until then, I will see you next class.